In this module, we continue our discussion of time response analysis. In particular, we look at second-order systems. So far in this semester, we've been doing what we term time response analysis. In the previous module, we looked at and memorized, in essence, the character of a certain type of system called a first-order system. In this module, we will look at a slightly more complicated system called a second-order system, and we will look more closely at the important property of stability. In Module 12, we will examine systems that don't have this standard form of a first-order or second-order system. Recall that so far in this semester we've learned how to determine the time response of a system for an arbitrary initial condition and a given input. In other words, we've learned how to solve differential equation and transfer function models of dynamic systems. In the previous module, we motivated why it's important, or why we might want to, in essence, memorize the response of some standard systems to some standard inputs. The motivation here is that by memorizing these standard, simple system responses, it gives us insight into more complicated systems and into the responsive systems to more complicated inputs. The character of these standard responses can also be used for black box modeling and for specifying requirements on an engineered system. In the previous module, we in particular looked at first-order systems. So first-order systems, their transfer function have this form where they get their name because there is a single pole. So since the system has only one pole, it's termed a first-order system. Such a system is defined by two parameters. Think back to what the names of these parameters are and what they tell us about a system's response. The parameter K is what we call the DC gain. It gets its name because it characterizes the amount of scaling of a system's output for a constant input. So in this case, we've given this system a unit step input, an input of magnitude constant 1, and the output is scaled by an amount k in steady state, thereby reaching that level. The parameter tau is called the time constant, and it characterizes the speed of response of the system. More specifically, the value tau tells us how long it takes for the system output to change 63.2% of its total amount of change. Looking at this step response, its character matches what we would expect based on what we've learned earlier in the course. In particular, we've learned that the output of a dynamic system is determined by the type of forcing input and the natural response of the system. So in this case, we're forcing the system with a step or a constant, so we would expect the output to have a constant in it. And since we have a single pole that must be real, we would expect the natural response to be exponential decay. And that's what we get here. We haven't discussed exactly what a second-order system is, but by extension you might be able to guess that it means a system that has two poles. And so if the denominator is quadratic, the poles do not have to be completely real. You can have complex conjugate poles. In such a case, you would have an imaginary part which tells us that the natural response oscillates. Therefore, if we feed a second-order system with complex poles a step input, this is the sort of response we're going to get. Where the output, again, has a constant due to the forcing input, but we don't just have exponential decay. We have an exponentially decaying sinusoid, because the poles have an imaginary part. In the previous two slides, we were reminded how the poles of a transfer function relate to the natural response of a dynamic system. In the case that we don't have a transfer function model, but rather we have a differential equation model, the roots of the characteristic equation tell us the same thing. And specifically, that's that the real part of the pole tells us the rate of decay if the real part is negative, or growth if the real part is positive, and the imaginary part of the pole tells us the frequency of oscillation. So recognizing this, think about what must be true about this system in order for its natural response to be stable. The property of stability isn't something we've talked a lot about, but we've mentioned it briefly. To remind you, the response is stable if it doesn't grow unbounded. So what must be true about the system in order that its natural response not grow unbounded? In essence, we need that the real part of the pole be less than or equal to 0, because if it's greater than 0, then we have exponential growth. If the real part is less than 0, then we have an exponential with a negative exponent, and we get exponential decay. If the real part is equal to 0, then we get an exponential with an exponent of 0, which is equal to 1, which means that the natural response neither decays nor grows. It either is constant or the amplitude is constant. So this is a basic definition of stability. There are some more nuanced definitions of stability that we're going to discuss briefly. One definition is called asymptotic stability, and it says, for no input and any initial condition, the output decays to 0 as t goes to infinity. So in other words, it's not enough that the natural response doesn't blow up, but it must actually decay to 0. Looking at this example mass spring damper system described by this differential equation for its natural response, for there being no forcing input, intuitively we would believe that this system is asymptotically stable. If we gave this system some initial condition, we took the block, the mass, and pulled it back and let it go, it would oscillate, but it would eventually die out, returning to equilibrium. Mathematically, the way that we can tell that is that the roots of the characteristic equation have negative real part. So it's not enough that the real parts be 0, where we get neither decay nor growth. The real part must actually be negative so that we get exponential decay. In this case, the condition is based on the characteristic equation and not the transfer function, because there is no input, and a transfer function essentially characterizes the response of the system to an input. What if our system has no B? So what if our system has no damper? Do you think it'll be asymptotically stable? Well, let's think about it for a second. So let's say that we had a differential equation where it has no x dot term, no b term. So in this case, the characteristic equation is lambda squared plus 4 equals 0. If we solve for lambda, we bring the negative 4 to the right-hand side and take the square root. The square root of a negative number is going to give us the imaginary number j. And the square root of 4 is 2. So we'll get 2j, where square roots always have a positive root and a negative root. So looking at this, the real part is 0, so we don't have exponential decay or growth. We do have an imaginary part, however, so we'll have oscillation of frequency 2. So we would expect the free response, or the natural response of this system, to oscillate forever without decaying. Therefore, the system is stable, but it's not asymptotically stable. The natural response doesn't grow unbounded, but it doesn't decay to 0 either. Another more nuanced definition of stability is something called bibo stability. And bibo stands for bounded input, bounded output. And its definition is that for zero initial conditions and bounded input, output x is bounded for all t. So as long as the input is bounded, the response of the system shouldn't blow up either. So let's look at, again, a mass spring damper system, except in this case, the system is actually forced by an input f, or a forcing function f. The conditions for bibo stability are very similar to those for asymptotic stability in that all poles of the transfer function, or roots of the characteristic equation, must have negative real part. So let's try and think about this case again where b is equal to 0. So if we had no damper, can you think of a forcing input that's bounded that will cause the output to be unbounded? So this is a little challenging, especially if you're not a mechanical engineer, but you can think of a system that has a resonance. So you can sort of imagine that if we forced this system at a frequency that's equal to the natural frequency of the system, we can cause a resonance, we can cause the amplitude to continue to grow and grow and grow. An example of this that we're all familiar with is you can imagine pushing someone on a swing. So if you push the person at exactly the right frequency, that is the natural frequency of the swing, you can make the person swing higher and higher and higher. In essence, you can make it go unstable. So just by pushing with a finite amount of force, you can make the swing go unstable. The same thing is true here. Therefore, if b is 0, again, it's stable, but it's not bibo stable. In this case, the requirements for asymptotic stability and bibo stability are the same. And the analysis of linear systems in general isn't that difficult. If the poles are less than 0, then we're stable, whether it be bibo stability or asymptotic stability. If the poles are equal to 0, or have a real part that's equal to 0, then we're sort of on the margin of stability. So in this case, we're not bibo stable and we're not asymptotic stable. And we're on the verge of being unstable. When the analysis of stability becomes really interesting is when you consider nonlinear systems. So in that case, with nonlinear systems, it's much more challenging. You can't even really talk about the system being stable. You need to talk about the specific type of input and the specific initial conditions. So a nonlinear system may be stable for a certain input but not another input, or it might be stable or at least locally stable for a certain set of initial conditions but not another set of initial conditions. We won't get into that too much, but that's really where a lot of the nuance comes in. At this point, we will now discuss the standard form of a second-order system. We had previously discussed first-order systems. Second-order systems are similar, except they're defined by the fact that their differential equation model has derivatives of order 2. So we have an equation with a function y, its first derivative, and its second derivative. U is the forcing input. These parameters, zeta and omega n, will be explained momentarily. If we take the Laplace transform of this differential equation, assuming 0 initial conditions, and rearrange it into the form of output over input, where we're assuming that y is the output and u is the input, then we get this standard form of the transfer function, where again the name second order comes from the fact that the polynomial in the denominator is a second order polynomial. We have 2 poles. The key parameters for defining this system a second order system, just like we did with the first order system where we had the DC gain and the time constant. Here we have omega n, which is the undamped natural frequency of the system. So this is the frequency that the system would oscillate with if it didn't have any damping. And zeta is called the damping ratio. And another way to think of this is that it's the ratio between the actual damping in the system and the amount of damping needed to damp out all oscillation. These will become more clear momentarily. Something else to notice about this canonical form, not only is it second order in that it has two poles, but also the numerator has the same form as the constant term in the denominator, where the leading coefficient of the s squared term is 1. So we have a numerator that's just a constant equal to this term, and there are no s terms in the numerator. We will discuss later how to characterize systems, even second order systems, that don't have this exact form, i.e. those that do have s's in the numerator. We can also rearrange this transfer function by completing the square in the denominator to get the transfer function in terms of two other parameters, sigma, which is in essence the real part of the pole, and omega d, which is the imaginary part of the poles. So looking at the denominator of the standard form of a second order system again, we can find the poles of this quadratic using the quadratic formula, where the a coefficient is 1, this is the b coefficient, and this is the c coefficient. And the poles can be found from the formula minus b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. This 2 cancels with the 2 in the denominator. In this term, we have a 4. When we square this term, we get another 4, which we can factor out and take the square root of to get a 2. And so that'll cancel with that 2, giving us poles of this form. Looking at this, the character of the response of a second order system will change fundamentally with the value of zeta. With a first order system, we always had one pole and it was always real. With a second order system, we can have complex poles, we can have purely real poles, we can have purely imaginary poles. And so the fundamental behavior of the system changes with zeta based on the type of poles that we end up with. So for example, if zeta is equal to 0, then this term goes away and this term goes away, and we have the square root of minus 1, and we basically have poles of plus or minus j omega n. So the poles are purely imaginary. That means that the response oscillates, the natural response of the system oscillates because there's an imaginary portion. And since the real portion is equal to 0, the oscillation neither grows nor decays. And so this is what we call an undamped response. If zeta is less than 1 but greater than 0, then what we'll have here is a negative number. And when we take the square root of that, we get an imaginary number. And so we'll have a real part to our poles and an imaginary part to our poles. So our poles are complex, and the natural response will have the form of a decaying sinusoid. And this is what we term underdamped. If zeta is equal to 1, then this term will go to 0, and we'll just be left with a single real pole. Or another way to think of it is two poles at the exact same location. And since the poles are real, we have no oscillation. So this is the point at which we go from having oscillation to having no oscillation. And so this is termed critically damped. If zeta is greater than 0, then this is positive, and we'll have a real number plus a real number and a real number subtracting a real number. And so we'll have real poles again, but they'll be different values. So we'll have two distinct real poles, and this is termed overdamped, where again we have no oscillation. On this slide, I'm going to go ahead and re-mention these different cases: undamped, underdamped, critically damped, and overdamped. Show examples of what the step response of these systems looks like. And I'm also going to plot the poles in the complex S-plane. So this is something that we're going to do a lot of going forward, is to look at the location of the poles graphically, where the horizontal axis represents the real portion of the pole and the vertical axis represents the imaginary portion of the pole. And this is something that we're going to get familiar with, and it's going to help us to quickly evaluate a system and predict its response. So recall, when zeta is equal to 0, our poles are purely imaginary. So we have a real part equal to 0, but an imaginary portion plus or minus j omega n. And so our response oscillates without decaying. And you get a response that looks something like this. So with a step input, we have a constant plus a sinusoid, and we get this shape. When zeta is greater than 0 and less than 1, we have complex poles. So we have poles that have a real part that's non-zero and an imaginary part that's non-zero. And so they're located in this portion of the S-plane. For the location where as they're plotted, the real part is negative, so we have exponential decay, and the imaginary part tells us the frequency of oscillation. So we get a decaying sinusoid added to a constant value, and we get a response that looks like this. When zeta is exactly equal to 1, we have a repeated real pole. So we have two poles on the real axis at the exact same location. Since we have no imaginary part, we have no oscillation, and we get a response that looks like this. This response looks very similar to a first-order system in the sense that there's no oscillation. The way that you can tell the difference between a first-order response and a critically damped response is at the origin, at time t equals 0. The slope starts off with a value of 0, whereas with a first-order response, the initial slope is non-zero. When zeta is greater than 1, the poles are still real, but now they're not repeated. So we have two real poles with no imaginary portion, or the imaginary portion is 0, but they're at different locations. And the response looks very similar to the critically damped case where there's no oscillation. Here again we show the complex S-plane with two poles plotted. We'll go ahead and again look at this in order to try to get a better sense of what these different parameters tell us about the system's response. So in this case we have two poles that are complex. So we have an underdamped system. In that case, our poles are going to have the form minus zeta omega n plus or minus j omega n times the square root of 1 minus zeta squared. And the derivation of this you can see earlier where we used the quadratic formula. In this case, the real part is equal to zeta times omega n. It's also called sigma. And so this tells us the rate of decay, presuming it's negative. So it gives us a sense of the speed of response of the system. The imaginary portion is called omega d. So this is the real portion. This is the imaginary portion. The real part is plotted on the horizontal axis. The imaginary part is plotted on the vertical axis. And again, the imaginary part tells us the frequency of oscillation, where omega d is also called the damped natural frequency. So this is the actual frequency of the natural response. It's the actual frequency with which the natural response oscillates. Omega n is not the frequency with which the system oscillates. This is what we call the undamped natural frequency. So this is the frequency the system would oscillate with if there was no damping. In the figure, omega n is the distance of the pole to the origin. Another way to see that, you can derive this equation by using the Pythagorean theorem, where omega n is the hypotenuse, the imaginary part, omega d, is one leg, and the real part, sigma, is the other leg. So, the hypotenuse is equal to the 2 legs squared, the sum of the 2 legs squared. A squared plus b squared equals c squared. So this relationship you can also use to derive the expression for omega d. We also then have this relationship, beta, where beta is this angle, and it relates to the damping ratio, zeta. And you can see this if you think back to what you've learned in trigonometry. Cosine is equal to adjacent over hypotenuse, SOHCAHTOA. So if in this right triangle, the adjacent side is the real part, zeta omega n, the hypotenuse is omega n. And so you get this relationship. Looking at this, a way to sort of get a sense by looking at this angle of how much damping the system has. If the system is completely undamped, it doesn't damp out at all, it oscillates forever, then beta is 90 degrees. Our poles are on the imaginary axis. If beta is 0, then we're on the horizontal axis and our poles are completely real, and so we're overdamped. This is something you can use to help you understand how this angle relates to response. When we're on the real axis, small beta means lots of damping, large beta, close to 90 degrees, means little damping. So this relates to damping. Something else to quickly point out, when we have complex poles, they always come in conjugate pairs. So we always have, if we have a pole in the S-plane, there's always a reflection of that pole where they have the same real part but a negative imaginary part. So they're reflected across the horizontal real axis. At this point, we're now going to derive the equation for the step response of an underdamped second-order system. And just was the case with the first-order system, we'll show longhand how to derive this response, how to find this response, doing partial fraction expansions, using inverse Laplace transform, but then we won't do it ever again. This standard response is common enough that we're just going to memorize the character of it. So recalling that we have a transfer function called g of s, and it has the form of a canonical second-order system. And we want to find, in essence, y of t. Looking at the Laplace transform of the input, where the input is a unit step, the Laplace transform is equal to 1 over s. Y of s we can find by multiplying u of s times g of s, by multiplying the input by the transfer function, where g of s has our standard form, u of s is the unit step. I'm going to go ahead and express that in the alternative form in terms of sigma and omega d, where we complete the square to get this form. Looking at this is something that we may not recognize from the Laplace transform table. So what we can do is we can do a partial fraction expansion where we have one real distinct pole, and then we have a quadratic, we have complex poles. And so if we keep the quadratic, then the numerator is going to have the form bs plus c. So we can find the values of a, b, and c in the same way that we've learned how to do the partial fraction before. I'm not going to go into that detail, but looking at this, we may recall that a system with this sort of denominator looks like basically a sinusoid that's been shifted in the s domain. So if we had s squared plus omega n squared, or s squared plus omega squared, that's either a sine or a cosine. And then if we shift it by an amount sigma, then that adds an exponential decay to it. In the case of a sine, we're going to want a numerator that's exactly equal to this, omega d. And in the case of a shifted cosine, we're going to want an s plus sigma in the numerator. So we've got this form, this is our decaying cosine, get this form, this is our decaying sine, and then when we solve for a, b, and c, the corresponding coefficients we get are a 1 here, a minus 1 here, and a minus sigma over omega d here. Taking the inverse Laplace transform, this is just a unit step, or a constant 1 starting at t equals 0. This is a decaying cosine, e to the minus sigma t times cosine omega dt. This is a constant that comes out front, and this is decaying sine, so e to the minus sigma t times sine omega dt. Therefore, that's what the output response of a second order underdamped system looks like for a unit step input. Rewriting that on this page, if we look at this as t, when t is equal to 0, we get e to the 0, which is 1, cosine of 0 is also 1, and sine of 0 is 0. So in essence, we get 1 minus 1 times 1, which is equal to 0. So at time t equals 0, we would expect our graph to start off at 0. As t goes to infinity, this is just going to oscillate forever, but this is going to decay to 0. So in essence, we're going to end up with a constant subtracting a decaying sinusoid. We get a response that looks like this. Looking at this, there are several important properties for specifying a system that come from its step response. And these parameters, omega d and sigma, or zeta and omega n, relate to these parameters of this step response that has this sort of shape, similar to how k and tau related to the shape of a step response for a first order system. So real quickly, I'm going to define a few of these properties. So one property is called the rise time, t sub r, and it's a measure of how long it takes for the system to go from 10% of its final value to 90% of its final value. We have the peak time, which is the time it takes for the response to reach its peak value. We have the settling time, which is the time it takes for the response to get within a window of plus or minus 2% of the final value. And then we have the maximum overshoot, which is the maximum value of the response over the steady state value of the response, which in this case is 1. So in the subsequent slides, I'm going to talk about these properties a little bit more, and I'm going to show how they relate to sigma, omega d, zeta, and omega n. One property that wasn't on the previous slide is something called delay time, which is the time required for the response to reach half the final value for the first time. This isn't a particularly important property. We're not going to use it at all in this class. Another property is the rise time, which was defined. In the previous slide, it was defined as the time required for the response to rise from 10% to 90% of the steady state value. There are different definitions of rise time. Sometimes people use the time it takes to go from 0% to 100% of the steady state value. But in general, you wouldn't want to use the 0 to 100% definition for all systems, in particular for overdamped systems. Because overdamped systems, they only approach the final value in steady state. In other words, as time approaches infinity, they never actually get to 100%. So this would be not a very useful definition. This property is quite important, and it's used to specify requirements or to characterize the response of a system or an instrument or a test. But we won't use it too much in this class, maybe here or there. A property of the underdamped second order step response that we will use a lot in this class is settling time. Recall that the definition of settling time is the time required for the response to reach and stay within 2% of the final value. And just as was the case with rise time, there are different definitions of settling time. Some people use 1%, some people use 5%, but in this class we're going to use a 2% definition. What we would like to do is we'd like to be able to estimate the settling time based on the parameters of the standard second order system. And the way that we're going to do that is based on the rate of exponential decay. So looking at this expression for y of t, this is the equation for the underdamped step response. And if we look at this, what we have is we have a constant and we have a decaying sinusoid which will decay to 0. And so in steady state, the steady state value of the response is 1, and we're going to estimate when we're within plus or minus 2% of this 1 based on the exponential decay here. Since e to the minus 4 is approximately 0.02, we can match these up. We can base the settling time on this. And so we can estimate settling time as 4 divided by sigma, or 4 divided by the real portion of the pole. When we had a first order system, the settling time was equal to 4 times the time constant, which is the same thing as 4 divided by the real part of the pole, because the pole for a first order system is 1 over tau. With the second order system, however, this relationship is only approximate, because this sinusoid is varying between a maximum value and a minimum value that's negative. So we don't necessarily know at this TS time where exactly we are in this oscillation. Furthermore, the amplitude of this oscillation isn't always the same. So this relationship is only an estimate for settling time of an underdamped second order system, but it tends to work pretty well, if not being a little on the conservative side usually. Another parameter that we will use a lot is peak time. It's the time required for the response to reach the first peak of the overshoot. And so again, we can get a relationship for this in terms of the parameters of the second order system by looking at the equation for the second order step response. So looking at this equation, recall, it has this sort of shape, and we want to be able to calculate when we reach the time at which we reach this peak. So take a look at that and think about it for a second, how we might be able to derive an expression for T sub p. Looking at this, when we have a maximum, like as we do in this case, the value of the slope is going to be equal to 0 at that maximum. That means that the derivative y dot, the derivative of y with respect to time, is going to equal 0 at that point. So what we can do is we can take the derivative of this expression and find the first time that it's equal to 0. So if we take the derivative of y, this 1 is just a constant, so its derivative is 0. And then we have this expression, which is the product of two terms. We have an exponential, and then we have a couple sinusoids. And we can take the derivative of that using the product rule, where the product rule is the derivative of the first term times the second term plus the first term times the derivative of the second term. And if we do that, this is the expression we get. This is the derivative of negative e to the negative sigma t. This is the second function. This is the first function. And then this is the derivative of cosine omega dt. And this is the derivative of sigma over omega d times sine omega dt. Looking at this term, sigma, when we distribute sigma e to the minus sigma t times cosine, is equal but of opposite sign to what we have over here when we distribute the negative e to the minus sigma t, multiplying the sigma times cosine omega dt. So when we sum those two, they sum to 0. We're left with this. Looking at what we're left with, both terms are left with a e to the minus sigma t, and both terms have a sine omega dt. So if we factor those out, we get this, where we're left with sigma times sigma divided by omega d, and then over here we're left with omega d. If we look at this, the exponential decays to 0 as time goes to infinity, but it never actually reaches 0. And this is just a positive number, a constant, so it can't equal 0. So in order for this whole term to equal 0, we need this to equal 0. So this term can't equal 0. So we're looking for when the sign is equal to 0. And it equals 0 at time equals 0, but that's sort of the trivial solution. But the next time it equals 0 is when omega dt is equal to pi. And so solving for t, we get the peak time is equal to pi divided by omega d. Another way to remember this is you can think of this as 1/2 of a period. A period is 2 pi divided by the frequency, and so half of a period is pi divided by the frequency. It's like the period is the time it takes to do one cycle, so from a minimum to a minimum, or a peak to a peak, and in this case we're going from a minimum to a peak, and so that's exactly half of one cycle. Another property that we'll use a lot in this class is maximum overshoot, and that's the peak value of the response as measured from the steady state value. We often represent it as a percentage. And so again, thinking back to what this looks like, the maximum overshoot is how much this peak reaches above the steady state value. So again, think about how we might get an expression for that in terms of the parameters of the second order system. So looking at this is in essence, it's related to the value of our response at the peak time. And so what we can do is we can plug in our value for t sub peak into our expression for y, and we know that that's going to equal the steady state value in this case, which is 1 plus the amount of overshoot m sub p. This is the expression for y. If we plug in pi over omega d in for t, plug it into there, we'll plug it into there, we'll plug it into there. Here the omega d's will cancel, here the omega d's will cancel. Sine of pi is like 180 degrees, that's 0. Cosine of pi, 180 degrees, is equal to -1. So using that fact, we have 1 plus mp on the left. On the right, we have 1 minus this expression e to the negative sigma times pi over omega d, where this negative multiplying this negative becomes a positive. That's what we get there. So going further, substituting in values for sigma and omega d, where sigma is zeta times omega n, and omega d is omega n times the square root of the quantity 1 minus zeta squared. The omega n's cancel. We have a 1 on the left-hand side and a 1 on the right-hand side. So we can subtract through by those 1s to get an expression for MP all by itself. We get that MP is equal to e to the minus zeta pi divided by the square root of 1 minus zeta squared. So an interesting thing to note about this is that the overshoot depends on only zeta. The only parameter of the second order system that the overshoot depends on is the damping ratio zeta. To summarize, we've gotten expressions for 3 of the properties of a second order underdamped step response in terms of the parameters of a standard second order system. So these second 2 expressions are exact, but peak time depends on omega d, overshoot depends on zeta. The settle time, this expression isn't exact for a second order underdamped system, but it's still a useful approximation, and it depends on sigma. Something to keep in mind is that the way that we derived these expressions was to use the response of the canonical second order underdamped system. So these relationships don't hold if the system is not second order, i.e. it has 3 poles or 4 poles, and it doesn't work if the system's not canonical. For example, if we have s's in the numerator. Despite that fact, these are still useful relations to know, and we'll discuss more how to address the situation when we don't have a canonical second order system. Now we will do an example where we plot the step response of this given transfer function. So one way to accomplish this is to do it in essence longhand. Multiply the transfer function with the input, do a partial fraction expansion, do an inverse Laplace transform, and so forth. But we actually don't have to do that any longer because we have equations that relate the shape of the second order step response to the parameters of the second order transfer function. Looking at this, think to yourself, does this have the form of the canonical second order system? It's close, but it's not quite. With a second order canonical system, we need a 1 in front of the s squared term, which we have, but we need this constant term in the denominator to equal the numerator, which we don't quite have. However, if we factor a 2 out front, then we have a numerator of 25 that matches the constant term in the denominator like we wish. And so the way that we can think of this, so we've got our canonical form, omega n squared in the numerator, s squared, plus 2 zeta omega ns, plus omega n squared in the denominator, and then just a constant k out front. Think about what the effect of this constant k is. In essence, this constant is just a scaling factor. The step response of this transfer function will look just like the canonical system here, except it'll be scaled vertically by an amount of 2. We can sort of think of this k as the DC gain, just like we had with the first order transfer function. So looking at the rest of it, let's think about how we might be able to estimate what omega n is, what zeta is, what sigma is, what omega d is, etc. The way that we can do that is by matching coefficients. So matching this term of our transfer function to this term, they're both the constant elements of the denominator. We can see that omega n squared is equal to 25. If we take the square root of both sides, we have that omega n is equal to 5. So that gives us our first parameter. Then we can do the same thing for the coefficient in front of the s term, where we have that 2 zeta omega n is equal to 6. We can solve for zeta by dividing through by 2 times omega n, where omega n is equal to 5. So 6 divided by 10 is 0.6. That gives us an expression for zeta. And then we can calculate omega d from the equation. Omega d is equal to omega n times the square root of 1 minus zeta squared, where omega n is 5, zeta is 0.6. If we calculate that out, we get that omega d is equal to 4. Now that we've estimated these parameters of a standard second order canonical system, we can then use those to estimate the shape of the second order step response. Using those relations from the previous slide, we know that Ts is equal to 4 divided by sigma, approximately, where sigma is zeta times omega n. So we have 4 divided by zeta, which is 0.6, times omega n, which is 5. We get that the settle time is approximately 4/3, or 1.33 seconds. Similarly, we have an expression for peak time, which is exactly equal to pi divided by omega d, where in this case omega d is equal to 4. So pi divided by 4 is approximately 0.785 seconds. So that's approximately what the peak time is. And then we can calculate overshoot as e to the minus zeta times pi divided by the square root of 1 minus zeta squared, where zeta is equal to 0.6. If we plug that into our calculator, that we get that MP is approximately 0.095. So looking at these values, these hold if our system were a canonical second order system. In this case, we're not quite a canonical second order system because of this multiplication by the scaling factor 2. So you can sort of imagine that the canonical response looks like this, with a steady state value of 1. By multiplying the whole thing by 2, we're going to get the same sort of shape, but everything's going to be scaled. And so the steady state value is going to be 2, but the peak time will be at the same location. Where we get within plus or minus 2% will be the same location. So the settle time is unchanged and the peak time is unchanged, but the maximum overshoot will be different. It'll be scaled by a factor of 2. One way to sort of avoid this confusion is to consider overshoot as a percentage. So while the overshoot may not actually be 0.095, it will be 9.5%, even with the scaling. So once we have these properties of the step response, we can roughly sketch the second order step response, or the step response of the given transfer function. Okay. So looking at this, we have this sort of standard shape of a constant added to a decaying sinusoid. The steady state value is going to equal 2 because of the scaling. The peak time will occur at 0.785 seconds. The overshoot is 9.5%. So 9.5% of 2 is 0.19. And so the peak is approximately 2.19. And we get within plus or minus 2% at around 1.33 seconds. So this is a very rough sketch of the second order step response, where this is the output y and the horizontal axis is the time t. This overshoot will be exact. This peak time will be exact. The settling time won't be exactly 1.33, but it should be relatively close. Another way that we can use these equations, these relationships that we've just learned, is also to sort of go in the reverse direction. So you can imagine if we did some experiment on a system and we were able to generate a step response experimentally, we could back out a model that would produce that step response. So in essence, we can do black box modeling. So we could look at a step response if it had this sort of shape, estimate the peak time, estimate the overshoot, use that to calculate the parameters, omega d, zeta, etc. This is sort of what we did in the previous module with the first order system. Doing a little bit more review, let's think about where pole locations will be that will give us the same properties. So looking at this, settle time is based on sigma. So in theory, if we had a system, or if we had a series of systems where all of the poles had the same sigma, had the same real part, then they should all have similar settling times. So here's sigma. So systems where the poles have the same real part will have the same settling time, or approximately the same settling time. Here we have that peak time depends on omega d, the imaginary part of the poles. So systems that have poles with the same imaginary part will have the same peak time. And here, systems that have the same zeta will have the same overshoot, where we can recall that zeta shows up in the graph in terms of the angle beta. So systems that have poles that have the same beta, that are along this same line in the S-plane, will have the same overshoot. And so this is just some practice to get used to thinking about looking at the poles in the S-plane and anticipating what it tells us about the response of our system. So let's do a little bit more of this. So let's think about a situation where our poles have the same sigma, the same real part, but increasing omega d, where omega d is the imaginary part. So you can sort of imagine we have the same sigma, but increasing omega d. And think about, what does that mean for the step response? Since settling time is approximately equal to 4 over sigma, if we have a constant sigma, they should have similar settling times. And since peak time is equal to pi over omega d, if we increase omega d, and omega d is inversely proportional to peak time, increasing omega d should make TP get smaller. So if we look at the step responses, they should have similar settling times. That is, they have the same sort of envelope, e to the minus sigma t. but the TP should get smaller. So initially, this is what our peak time is, but as we increase omega d, the peak time gets smaller and smaller. Okay. And so one reason that we might want to do this, not only for sort of predicting the response of systems, but this is also going to help us when we go to design controllers. We want to know how to add control in order to move the poles of our system around. In this case, we can see that if we move our poles up, we will get a similar settling time, a similar envelope of decay, but the peak time will get smaller. In essence, our system response will get faster. Here, let's look at the situation where sigma is increasing, but we keep omega d constant. So think about how the poles would move in the complex plane for this case. Since omega d is the imaginary part, all of the poles should have the same imaginary part. And since sigma is the real part, it should have an increasing real part. In other words, the poles should move farther to the left. So in actuality, this is negative sigma. These should have the same omega d, and the minus sigma moves to the left. Sigma is getting larger. Looking at this, think about how the response in this case changes. Since the omega d is constant, the TP should also be constant. But since sigma is increasing, the settling time should go down. The rate of exponential decay should be greater, should decay faster. And that's what we see here. So all three have the same peak time, but you can see for graph 1, the blue line, it takes a while for the oscillation to die out. For 2, it dies out faster, and for 3, it dies out very quickly. And then finally, let's look at a situation where omega n is increasing and zeta is constant. So think about what that means in terms of the movement of the poles in the complex plane. Zeta relates to the angle beta, so that means beta should be constant. And omega n is the distance from the origin, so that means that we should move on a constant beta angle away from the origin. So they all have the same beta, but the omega n is increasing. And so thinking back to how overshoot is a function of only zeta, that means that all of these step responses should have the same overshoot. But let's think about how does TS and TP change. So as the poles move to the left, that means sigma is getting larger. So that means that the settling time is getting smaller. Furthermore, they're moving up, which means the imaginary part's getting larger, which means omega d is getting larger, which means that the peak time is getting smaller. So if we actually look at the step responses, you can see they all have the same overshoot, but the peak time gets smaller and the settling time gets smaller as well. In essence, the response gets faster. So that gives us a fair bit of work with underdamped second order step responses. So let's go ahead and derive what the response is when the system is overdamped. So recall, what does it mean? How do we know if a system is overdamped, our second order system is overdamped? One way to tell is that zeta is greater than 1. Another way to tell is if the poles are real. So we'll again go ahead and work this out longhand, but this is basically the last time we'll do it. Since our input is a unit step, the Laplace transform of a unit step is 1 over s. That's what u of s is equal to. We can calculate the output y of s as the transfer function times the input, where our transfer function has the form of a canonical second-order system. Our input is the unit step. Since we're overdamped, we have two distinct real poles, which we can factor out. So let's say that one pole is minus a and another pole is negative b. We can factor those into two distinct factors. And it turns out in order to have this numerator matching this constant term, we need an ab in the numerator. Looking at this, we can do a partial fraction expansion. We've got three poles. They're distinct and real. So this is like case 1, where each of the residues or each of the coefficients are real numbers. We're not going to go through the details of finding a, b, and c, but if we did, it would turn out that this is what they're equal to. A is equal to 1, capital B is equal to little b divided by a minus b, and capital C is equal to negative a divided by a minus b. We can go ahead and take the inverse Laplace transform of this. The inverse Laplace transform of 1 over s is a unit step, or a constant 1 starting at t equals 0. The inverse Laplace transform of 1 over s plus a is e to the minus at. We just have this constant out front. The inverse Laplace transform of 1 over s plus b is e to the minus bt. We just have this constant out front. We again make the assumption that this doesn't begin until t is equal to 0. So looking at this, we have a constant plus decaying exponentials. Therefore, this looks very much like a first-order system. The only difference is the behavior at the origin. So this brings us to the conclusion of Module 12. The first thing we did in this module was examine the property of stability. In essence, stability is the most important property to be met when you're designing a control system. At the very least, you need your system to not go out of control. We looked at two very specific notions of stability, asymptotic stability and bibo stability, where asymptotic stability means that the natural response of the system decays to 0. It's not enough that the natural response doesn't grow unbounded, it actually must decay to 0. And bibo stability is defined as bounded input, bounded output stability. So as long as the input to our system is bounded, that means that the output of our system also needs to be bounded. We then looked at canonical second-order systems. There are 3 specific cases. Well, actually, there's 4. There's undamped, underdamped, critically damped, and overdamped, where the behavior of each of these different cases are fundamentally different and change based on the value of the damping ratio zeta. And then we looked at the second-order step response, in particular the properties of settling time, peak time, and maximum overshoot, and we related the parameters of the step response to the parameters of the second-order canonical system, zeta, omega n, etc.